Something unusual just came out of Shanghai. A compact 4-foot robot with a split artificial intelligence architecture, 2 separate brain systems running inside one body simultaneously. One brain thinks, the other one moves, and they never interfere with each other. This dual brain design solves a problem that has been quietly holding humanoid robots back for years, and the engineers at Jaka Robotics just cracked it wide open. Jaka Robotics unveiled a humanoid called Pi. It stands 4 feet tall or 1.22 meters and weighs around 92 pounds or 42 kilograms. Those dimensions make it significantly more compact than the full-scale humanoids most people are used to seeing. But the size is not the story here. The architecture is. Pi has 27 degrees of freedom and uses newly developed integrated joint modules that are 15 to 27% smaller than Jaka's previous generations. Smaller joints mean a lighter body, cleaner movement, and less mechanical drag throughout every motion cycle. The knee joints deliver up to 120 Newton-meters of torque, giving the robot enough strength for stable walking and controlled movement under load. Each arm carries up to 3 kilograms, which lets Pi handle objects, run manipulation tests, and interact with the physical world rather than just walking around as a demonstration piece. Now here is the part that changes everything. Jaka built Pi's core intelligence on Intel's heterogeneous computing platform and deliberately separated 2 types of intelligence into 2 distinct systems. The higher-level system works like a cerebrum. It handles AI reasoning, vision perception, large language models, application logic, and the general understanding of what the robot is supposed to do in a given situation. The lower-level system works like a cerebellum. It controls real-time movement through an EtherCAT-based control network operating at millisecond-level latency. Why does that separation matter? Because humanoid robots need 2 completely different types of intelligence operating at the same time, and those 2 types of intelligence have fundamentally different requirements. The thinking brain needs time to reason. It processes language, evaluates the environment, forms a plan. The movement brain needs to be fast and deterministic. It cannot afford delays. When a robot is mid-step on uneven ground, the balance system must react in milliseconds without waiting for the reasoning system to finish a thought. By splitting these 2 systems, Jaka gives Pi the ability to hear a request, understand what is happening around it, plan a physical response, and execute that response through control systems that stay reliable at the movement level regardless of how long the reasoning side takes to process. 1 body, 2 minds, each doing exactly what it is best at. Jaka was founded in Shanghai in 2015 and built its reputation on collaborative robots used in industrial automation. Its existing lineup spans the Zoo series for assembly, machine tending, palletizing, and packaging, the Pro series with IP68 rated protection against dust, oil, and water, the S series with high accuracy force sensing, and the AL and A series combining robotic manipulation with machine vision. Pi represents a major strategic expansion from industrial arms into embodied AI platforms that can work in flexible, human-facing environments. The second development shifts the entire conversation geographically. Vietnam has now officially entered the humanoid robotics race, and it entered with 2 robots simultaneously. Vin Big Dynamics unveiled Dino, the company's first humanoid robot, at ICRA 2026 inches, Vienna and Computex Taipei 2026. Dino combines advanced AI, environmental perception, autonomous navigation, situational awareness, human-robot interaction, and dexterous manipulation in one platform. The company is targeting 2 very different use cases at the same time: security and surveillance in urban areas, campuses and commercial spaces, and household assistance for domestic environments. That dual ambition is technically demanding. A security robot needs long operational stability, reliable navigation, and consistent interaction with people in open, unpredictable environments. A household assistant needs safer movement, more precise object handling, and the ability to navigate messy everyday spaces. Building one platform that handles both requires solving very different engineering problems simultaneously. At Vinpearl Safari Phu Quoc, Dino was deployed as an autonomous robotic guide operating in outdoor conditions. It used multilingual speech, responded to visitors through natural language, and relied on real-time environmental awareness to answer questions and guide people through crowds, lighting changes, and unpredictable movement. That is a serious test because outdoor service environments expose weak points in navigation, speech processing, and perception timing that clean laboratory conditions never reveal. Behind Dino, VinDynamics also showed the VDM80 actuator joint, a compact motor system weighing less than 1 kilogram and running on a standard 48-volt power supply. It supports industrial communication standards including CAN FD, RS485, and EtherCAT. It reaches speeds of up to 235 revolutions per minute and carries an expected operational life of more than 10,000 hours. The company also presented a human-like robotic hand with 11 moving joints and 6 actively controlled degrees of freedom, with integrated force sensors for accurate grip control on delicate tasks. From the same Vin Group ecosystem, Vin Robotics unveiled VRH3, its third-generation humanoid, also at ICRA 2026 and Computex Taipei. VRH3 targets industrial automation, material handling, and work in complex environments. It has more than 31 actuators for coordinated whole-body movement and runs on 2 onboard edge computers for local processing without depending on remote systems. That local computing capability matters for low-latency decision-making in industrial settings, where any delay can make a robot unsafe or completely useless. VRH3 can transport objects, handle payloads of 6 to 8 kilograms, and perform assembly operations. Vin Robotics says all key technologies were developed in-house, including the mechanical architecture, real-time computing infrastructure, electrical architecture, power distribution platform, battery management system, and full-body AI control framework. That vertical integration gives the company precise control over how hardware and software interact, which pays dividends when improving balance, manipulation, energy efficiency, and reliability across generations. At ICRA 2026, Vin Robotics demonstrated VRH3's teleoperation system using motion capture technology built directly into a virtual reality headset, allowing an operator to control the humanoid in real time without any external tracking equipment. NVIDIA is taking a different approach to humanoid robotics. Instead of launching a finished robot, it unveiled the first open humanoid reference design built on its Isaac GR0T platform, giving researchers a complete hardware and software foundation for developing advanced robots. The platform is based on the Unitree H2 humanoid, a nearly 6-foot-tall robot with 31 degrees of freedom. NVIDIA added dual sharp-wave 5-finger tactile hands, increasing the total to 75 degrees of freedom and enabling sophisticated manipulation tasks beyond simple walking and movement. Its sensor suite includes stereo vision, wrist-mounted cameras, and motion tracking systems. The robot can carry up to 15 kilograms and delivers powerful torque for both arms and legs, supporting demanding real-world applications. At its core is NVIDIA's Jetson AGX Thor T5000, powered by a Blackwell-based GPU, a 1/4-core ARM CPU, and 128 GB of unified memory. This allows the robot to process sensors, control movement, and run AI models in real time. The system integrates with Isaac GR0T, covering data collection, simulation, training, testing, and deployment. Leading institutions such as ETH Zurich, Stanford Robotics Center, and UC San Diego have already adopted the platform, highlighting NVIDIA's goal of accelerating humanoid robotics through open, shared research infrastructure.